All right, so let's look at chain rule. That's where we ended last time in class, in person. Well, we ended with this, with the motivation for it, in that if we have linear functions, then linear functions are their own derivatives, and the so the derivative of the composition is the composition of the derivative for linear functions, right? Because if I have these two, a and b are two linear functions, and here x and y and z are just some Euclidean spaces Rn. Then if we have a and b, I can compose them BA, right? The derivative of A is A, the derivative of B is B. The derivative of BA is the composition of BA. It's BA, right? It's back itself, right? And the same thing works for differentiable functions, right? If I have just any open set U and a differentiable function or differentiable at P, and let's suppose that there is the image of U under F is inside some other open set V, right, where I have another differentiable function G defined on V, right? So I can now compose them, right? I can compose G with F, right? I can plug in F into G, right? So I can write down this composition. Let me call it capital F, right? And let's suppose that G is differentiable at whatever the image of P is, right? At Fp, right? Then the conclusion is that this composition is differentiable at P, right? And that its derivative is the composition of the derivatives, right? I mean, it's the derivative of F, capital F at P is the derivative of G, composes the derivative of F. Now, these have to be applied at the right points, right? So the derivative of F, little f, clearly has to be, you have to look at P, the derivative of G. Well, that makes sense at f of p, right? So that has to be applied at f of p. But really, f prime is, or capital F prime is little g prime composed with little f prime, right? That's really what we're saying here. Okay. So that's again repeating what I said. Right? If you don't write down the points, that's what it is, right? The derivative of the composition is the composition of the derivatives, right? Okay, so let's prove this, right? So to make things simpler, let's call A the derivative of f and B the derivative of g at the respective points, right? Now, we're gonna, there's gonna be sort of two things that move. Well, really one thing, the other will move with it. But h, that's gonna be like a little, a small move in Rn. And remember, Rn is where f is. I should really just get rid of all these. This Rn is where f is defined, right? It goes into Rm, right? And that's where g is defined, right? That's in Rm, and then that goes into Rl, right? So those are the those two guys, right? So h is now a little moving off of P a little bit in Rn, right? Now, so we're gonna we're looking at P plus H and P, right? So now let's look at let's give some other names. Let's write Q as f of P, and let's write K as f of p plus h minus f of p. And I just noticed to follow the convention in this book, I'm defining Q and K, right? So that's a small typo, right? But that's what they should be, right? So I'm just making, just naming these, right? So this is Q is the point where P goes under F, and K is how F moves as H moves, right? If we're gonna P is fixed, of course, right? And I do a little displacement in Rn in the domain, and that displaces where F goes, right? And so that displacement I'm gonna call K, right? And now let's look at the remainder for F, right? So I'm going to call it R of H, and that's just what it is, right? All right. So this is K. So really, I have that the remainder is K minus AH, or I could solve for AH. Then it's K minus R of H, right? So far, I'm just putting in names, right? Now, another thing like this, if I just rewrite this guy over here, it's getting a little bit too crowded. If I rewrite this guy over here, I can solve for, f of f of P plus H in terms of Q, which is f of P, and K, right? So let's look at the thing that we need to go to 0, right? I mean, if capital F is supposed to have derivative BA, right, then this is the thing that we need to go to 0 as H goes to 0, right? That's just from the definition, of derivatives, right? So you write down what this is, right, in there, right? That's just writing down the definition of capital F, right, over here, right? Now what we use is there's f of P plus H. We know that's Q plus K, and f of P, that's just Q, right? So we have that this becomes this, and this becomes this, right? So let's clear that, right? So that's what happened to this bit of it, and now I also replace the AH with the K minus R of H, right? So that goes in here, right? So that's what I did over here, right? So now we're in this bit. Right, that's this part of the so far not estimate, but so far it's an inequality, right? So now let's do triangle inequality, right? So I know this sort of looks like the thing that I know goes to 0. Well, maybe not with this, but sort of if this was just B of K and K was the the little displacement, then this sort of looks like the definition of the derivative of G. So let's try to isolate that, right? And let's move this guy into a separate term using the triangle inequality, and actually the inequality for operator norms, right? It's really B of RH, right? And then I separate out the norm of B as well, right? So I'm separating out that part of it. Of course, it's multiplied by B as well, right? And then in the first bit, I sort of almost have something that looks right. It doesn't quite look right. It's over norm of H. That's not good. But that's I can deal with it, right? I'll write down K, and let me just put down what K was. K was this, right? That's what it was by definition, right? That's how I defined K, right? So now I have all sorts of good things. This guy I know goes to 0, right? So this also, that's the remainder for f. I know that this goes to 0, the r of h over h, right? That goes to 0, again, by definition of differentiability of, right, I mean, it's basically just this over h, right? We know that that goes to 0. So because f is differentiable. Now, it doesn't quite yet say that this goes to 0 because it's multiplied by these guys, right? This and this, right? Over here, this is easy. The norm of b, that's a constant, right? So so a constant times something that goes to 0 goes to 0, right? So that part of it is fine. So we really need to worry about this. So as long as this is bounded, right? Because if it's bounded times something that goes to 0, that will go to 0, right? So we need to show that this is bounded. It's not quite the the thing that goes to 0 because it's the minus AH is missing here, right? So it's sort of looks like the thing that goes to 0, but without the AH, right? So it's not going to go to 0, but it's going to stay bounded if f is differentiable. Well, why? Well, let's look at what it is, right? Now, I could subtract and add the a minus h, right? So I have this using triangle inequality plus this, right? That is a bound from above of this guy. Now, this first term, right, just by knowing that f is differentiable, this thing goes to 0, right? So that goes away, right? And so I just have this, right? Wow, what is this? That's basically, the supremum of this is the norm of A, right? Over all non-zero h, right? And we are assuming that h is non-zero, right? Otherwise, none of this would have made sense, right? I mean, we are trying to look at this, right? I mean, where we started, we definitely need h to be non-zero, right? So maybe didn't mention that immediately, but right. So we have that this thing is bounded by this guy, which goes to 0, plus some constant, right? So it's definitely bounded, right? As h, for sort of for small enough h, right? I can make this to be arbitrarily small, right? So I can make it less than 1, let's say. It doesn't really matter, right? Anything. So for small enough h, this is bounded, and it's plus a constant, so it's bounded, right? And therefore, if it's something that goes to 0 times something is bounded, that goes to 0. Same thing over here, right? That goes to 0, meaning, what does it mean? It means that this guy went to 0. What did that mean? That meant precisely that the derivative of capital F at P was B composed with A, which is what we wanted. All right, so let me, instead of recording one long lecture, let's stop this here, and I'm gonna record another lecture in just a moment. But just so that we have nice small bits, right? So that was just the proof of the chain rule in several variables.